Hello, this is Kyle Codes, episode 5, I believe. So I watched one of my previous videos, and there's a section on hash tables, and on rewatching it, I realized that it made no sense. So I'm going to do another video on hash tables, kind of go into more detail. So let's begin that. Okay, so a hash table is a good solution to the problem of retrieving data, storing and retrieving data. Basically, you're faced with a problem where you're asked a question that can be answered by searching a set of data. So a good question that could be, a good example of this would be, given a person's name, what is their job? So if you were to say, my friend Kathy, what is her job? Well, I don't know what her job is. So the way we would do something like that, typically, without much thought into it, is create a list of all our friends, put them one after the other, like so, and we would search through each friend and find Kathy and then return the job that she does. So the question is, what is Kathy's job? So let's look through the first element. We'll iterate through these because they're a list. We'll say, first one is John. Well, that's not Kathy, so I'm going to skip that. Next one, Bill. That's not Kathy. Skip that. The next one is Kathy. Okay, that's her. So what is the corresponding job value? And that is teacher in this example. So I would return teacher, and I'm done. Now, you can kind of see a problem arising with performance when this list gets very long. And if you were to ask, what is John's job? That's a very simple question, because you go to the first element and you find John, and you say, John's a baker. But if you were to ask what Frank's job is, or if you have a list of 100 things and you're asking, what is the last person's job? This approach of iterating through each item is not going to be very useful. It's going to be slow. It's useful, but slow. So there's a couple ways you can solve this. One of them we kind of looked at before in one of the other videos is a binary search, where if you sort all your friends by their first name, then you can easily do a binary search, cut the table in half, and that's quicker than doing a scanning search. Another thing we can do is use a hash table. And so the way that a hash table works is by creating buckets, and you store items, key value pairs, like we had before. Bill is the name and the job is farmer. So you would store that in the bucket, and you can put an arbitrary amount of things in each bucket. And we have a quick function that allows us to get from a first name key to the bucket, where we can then search what is in the bucket. So that kind of cuts the search down. So in this example, you can see if I know which bucket to look in to find John, I can immediately go there and look at the first element in the list. And that only took, 2 operations. Go to bucket, read first element, good. So I'm just going to read through some of this stuff that I wrote earlier. So our basic algorithm is we're going to place the names in the buckets and label each bucket so that we can easily go from a key, which in this example is a person's first name, to a bucket. How we get from a key to a bucket is by using a hash function. And that'll become clear later as we implement it. In this example, the hash function is just to grab the first character of the key. So if you look at this, this example right here uses a hash function of just grabbing the first letter and going to the bucket for that person. So this is the B bucket because Bill's in here. This is the J bucket because John's in here. This is the C bucket and F bucket. Now, this is all pretty high level and conceptual, kind of abstract. In a real world implementation, it wouldn't be like this. It doesn't really make a lot of sense to have B, J, C, F. You'd probably have an alphabetical list, but we'll get to that later. What else is worth saying about this? Not much. So hopefully you kind of get the general idea of it. Oh, one thing I wanted to mention is there's a great example of a sort of hash function, not really a hash function, but it can be, it's very comparable if you think about the filing cabinets at your local doctor's office. Now, if you've ever gone into your doctor's office after hours and looked up your own records or the records of others, then you know exactly what I'm talking about. They're broken up into sections based on the first letter of the person's last name. So there's a section, there's possibly a filing cabinet just for A or A to E, and that's very helpful for humans because all you have to do is a simple computation, not even a computation, you just look at the first letter of their last name and you know the general area where you're going to go. Now, if there was if that wasn't there, and it was just a single file cabinet, just and everybody's records were jammed in there with no organization and no divisions, no buckets, you could call them, then you would just have to scan every single record until you found that person's record. So that's kind of comparing it to a real world example, and I'm sure you do stuff like that in your own life. Maybe in your contact book, you organize it by person's first or last, probably last name, the initial of their last name. You might have a separate bucket just for a very common last name, such as Smith, or other names. Okay, so I think that keep the doctor's filing cabinet in mind, and that organization, because that's a great analogy to help you understand how a hash table works in general. And the main difference between a hashing function that your doctor would use to find his patient's records and the hashing functions a computer would use is the hashing functions a computer uses are much more efficient because you can do some mathematic calculations on the person's name. So you could sum up the characters in their name, and whatever that sum is, that might be a better hashing function to more equally spread out names and make it easier to find. But a doctor is probably not going to want to add up the values of a person's name before searching for the filing cabinet labeled 689 or whatever. So yeah, let's make a simple hash table. Okay, I had some complaints from my 0 subscribers on the previous episodes that it wasn't zoomed in enough, so you couldn't really see the code well enough. So I'm going to zoom in a bit more, and hopefully that'll help. So let's start at the very top. What is our goal? So our goal is we want to create a hash table. We want to store a set of first names, set of people's first names and their jobs. And then somewhere later in the code, so I'm just going to put a lot of code. This is, if in a real world application, you probably have a lot of code between storing and then searching, and because you probably store their name as the contact record was created, and then later when you want to return to read data on it, you'd probably return at that point later on in the application to retrieve it. Otherwise, why store it at all? You can just keep it in memory. Well, it's probably going to be in memory anyway, but you could just keep it in a variable. Okay, so a lot of other code probably happens here. And now we want to retrieve someone's job based on name, because we're going to use it in the application based on their name. Okay, so let's do this. Kyle's hash table equals new Kyle's hash table. We haven't defined that yet, so it's an error. Okay, let's store name from the previous example. What did we have? John the baker. So that's our key is his first name, and the value is baker. Store. What was the other one? Bill the farmer. Kathy the teacher. And Frank cashier. Okay, now some stuff happens here, and then later on we want to call hash table retrieve, and we want to get Frank's job. Okay, so let's implement a hash table, a simple hash table. Oh, I don't need that. Class cows hash table. Okay, so based on what we know that we're going to need a set of buckets. Kyle's buckets. Kyle's bucket array. It's going to be an array of Kyle's bucket. Buckets. We're going to need, and because it's an array, we want to keep track of the size. We're going to probably need that later on. So we're going to have a number of buckets. We have a constructor, and I'm just going to set Kyle's buckets to a new. Oh wait, this is an array. We're going to use number of buckets and number of buckets. I don't actually know what we're going to set that to yet, so I'm just going to set. I'm just going to leave it, I suppose. I'll comment this out for now because I don't know what I want to set that to. Okay. So let's create a Kyle's bucket class, and I'm going to make this a private class because it's only going to be used by Kyle's hash table. I don't want anyone else to know about Kyle's bucket. Only the hash table, because it's used internally and no one outside should know it really exists. And what is a bucket? Let's look at kind of our spec, or our abstract idea of it. Well, it contains a list, possibly. Suppose we have... That's not right. Suppose we have 2 values in here, and instead of John, this is Jim, because this is our J bucket, so ideally we want to be able to store a list of items. So what is it? It's a list of string and string key value pairs. Okay, perfect. And do we need to know anything else about it? I don't think so. Just looking at this, it's just basically a list of key value pairs. Okay, so we're going to create a list of key value pairs. And the key is a string, which is the person's first name, and the value is a string, which is their job. And we're going to call it items. Let's set a constructor. It will say items equals new list of key value pair string string. Good. Clean up the code a little bit. Okay, Kyle bucket. We now have that defined. So let's get into the nitty gritty. So we called 2 functions over here, right? Store, and it took 2 strings, and it just stored it in the hash table so we could retrieve it later. So and that is a public class because it's being used by the calling code. So it doesn't need to return anything. It's just a procedure. It's just executing code. There's nothing returned. String. This is going to be first name, and the second string is going to be job. And you could abstract this a bit and call this the key, and this the value, So it could hold any two sets of strings. It's just a mapping of string to string, but because we're doing a specific implementation, I'm going to call it first name and job. That could be a bad practice. Might want to avoid doing that. You might want to keep it abstract so you can reuse it in other parts of the code, but for now, we have one use of it, so this is fine. But if later we wanted to use it to store a mapping of a person's last name and their social security number, then we would possibly go back into our Kyle's hash table, rename some stuff to make it more clear that it's a mapping of two strings, any kinds of strings. But for now, this is fine. Okay, so what do we do when we store it? Well, we want to find the correct bucket. And now, if you recall, in the PowerPoint presentation I was doing, how we get from a key to a bucket is by using a hashing function. And that basically takes a key and returns a bucket index. So what is the position of the bucket in the array? And this will make a bit more sense later as we retrieve things. It'll make a bit more sense. Okay, so what we want to do is get our bucket index equals our hashing function called first name, pass first name, which is the key. Now we have our bucket index. We're going to implement this later, so don't worry about the error. So we want to get oh, and I'm going to make this private because no one needs to know what that is. No one needs to know what this is either. Okay, so Kyle's buckets is our list of buckets, and we're going to get the one at bucket index. Now this is going to return a bucket. Okay, good. Now when we create, so right here, I think we can create this now. Oh, right. I'm just going to set it to 5 for now. 5 buckets. So we need to be wary that our hashing function returns a number from 0 to 4 because there's only 5 buckets, and we don't want to have an index out of bounds exception. So we have our bucket at index whatever. Now when we did this initialization, we only did a quick array initialization. We didn't actually set each element to a new bucket. So what we're going to do first is, if bucket equals null, to prevent null exceptions, we're going to set that element, Kyle's bucket, at bucket in Kyle's buckets at bucket index to a new Kyle's bucket, which will create everything we need because we put that in the constructor. So the constructor is inaccessible due to its protection level, so all we have to do is go down here to the constructor, make it public so people outside of the class can see it. Good, outside of Kyle's bucket class can see it. And Kyle's hash table is outside of Kyle's buckets class. Kyle's bucket class. Okay, so now we have this. We also, this is still null though, so we probably want to also assign this to the result of this assignment, which will be this. It will return this after it assigns it. Well, actually no, bucket will then be reference to this, I believe. Okay, bucket dot items dot add new, well, let's look at this, inaccessible, so we also need to make this public, or create some, or make it private and create some other functions, helper functions that give limited access to adding or removing items from this list. But let's just make it public for this example. So we're going to add, what does it want? A new key value pair. What do we do? Our key is our first name and our value is our job. Okay, so now our bucket contains that. So that looks good. Now let's do the retrieval. Public, and we're retrieving a string, which is the job. So I'm going to say Frank's job equals hash table retrieve Frank. Given the key Frank, retrieve the job for him. Okay? So we're going to return a string, which is job, retrieve, pass it a first name or key. Those are interchangeable. So the first thing we need to do is find the bucket index, again, where our hashing function tells us this first name is located. Okay, now we have the bucket. So we're going to, how's bucket equals buckets, what? Oh, how's buckets? Okay, I should have named that more clearly. Which is at bucket index. So we're getting the bucket at bucket index. Now, we need, because of the algorithm we're using, we don't initialize to save space and perform a bit of performance. We don't initialize the buckets in the list until we're storing something in it. So we need to do a null check, otherwise a bucket could not exist yet, because nothing's stored in there. So first we check if it's null. And what we want to do is, if it's not null, continue. Otherwise, we can return a null string, because that's our return value, a string. And if it's a null string, then that tells you that basically, back in this program that uses the hash table, if it returns null here when you call retrieve, Frank was not found in our hash table. So, okay, this is looking pretty good. Now, if the bucket is not null, that means the bucket exists. We're going to iterate for each, well, it's a key value pair of string and string, and we're going to call it item in bucket.items. So we have to iterate. Now, to make it more clear, go back to the PowerPoint. Look at this bucket in particular. It has John and Jim. So if we are given John, we're led to the J bucket, which is this one, and we then have to look at all the values inside the bucket. So it's another list iteration, but it's a smaller list iteration than looking through every contact. So kind of like at the doctor's office, instead of looking at every single patient's record until you find John Smith's patient record, you can go straight to the J file cabinet, or the S if you're doing by last name, and find the Smith file, and then go to John Smith in there. So that basically it's reducing the number of items you have to scan, which is a good goal. That means that's a performance increase. And the more you can reduce the scanning, the better the performance is. So the more accurate our hashing function becomes, the better our performance of our application will be in terms of retrieving items from the data structure. Okay, so for each item, we have an item which has a key and a value, because it's a key value pair. The key is the person's first name. So what we want to do is, if our bucket's item key equals the person's first name, we just want to return the item.value, which is going to be their job. And that should basically cover it. So the only error I see right now is our hashing function is not defined. So let's do that. Actually, I don't know why I called it our hashing function. I'm going to change it to my, because you're not helping me code. And we're going to have to return an int, which is an index in our array, in our bucket array, given a first name or key value. Okay, so there's a bunch of ways we can do this. Many ways we can do this. There's much debate, much arguing. There's more efficient ways, there's less efficient ways. We're going to use a pretty inefficient way, but that shows you the concept, and you can kind of extrapolate from there to find better hashing functions, especially if you have a mathematical mind, more so than I do. That will set you ahead. So for now, let's use the first letter, kind of like we were doing in the picture, and the way that doctors do it. Well, doctors use last names. Let's use the first letter of the person's first name. So we need to return what is it? A value from 0 to 25, right? Because there's 26 letters in the alphabet. So return first name. We're going to get the first letter and first name is a string, which is a character array, so we can use the character. We can get access to a character at an index by using this notation. Now we're going to do lowercase char.toLower because we don't want to deal with uppercase. So now we have a value from A to Z lowercase. Now that is actually a int value, which is not 0 to 25. It's going to be some value. I think it's somewhere in like 20s or 50s or something. So we actually need to subtract the value of A to get it to a 0 to 25 value, and this is lowercase a because that is the start of our range. So this, I think, might work. I'm not really 100% sure if it's going to work. There's an implicit cast here. I'll make it explicit because it might confuse people if it's not there. So we're casting the char, which is, if you look at this tooltip, represents a character as a UTF-16 code unit. That is, I believe, well, let me pull up the C# spec for char. The char type is classified as an integral type, but it differs from the other integral types in two ways. There are no implicit conversions from other types to char, blah, blah, blah. In particular, where is there anything? There's nothing useful here. I'm trying to find a reason that we can convert char to int. Okay, wait. Okay, I can't find it. So that was a waste of time. But a char can be converted to an int because it's stored as an int. 16-bit? Is that what it said? 16-bit integer? So hopefully this is pretty straightforward. If it's not, pause the video and just read this 1,000 times until this makes sense. It should make sense. Otherwise, I'll do another video. But I think this will work. Now, the problem is, before we start calling this, you could see it's possible that first name is null, and then we'd be calling the indexer on a null string, which would cause an exception. If the length is 0, that would also cause an exception. So let's do a check real quick before we start doing crazy stuff. And do if first name no, I'm gonna restart. If not string dot is null or empty first name, then we continue. Otherwise, we're going to return a blank string. So a better way to do that is just do if string is null or empty first name, return 0. So another case that could happen is our first name starts with a character that is not in the alphabet. So we should prepare for that as well. Let's see if there's a function that can help us with that. Alpha. Let's see. I'm going to pause the video and look up the function that we should be using for that. Give me a second. Okay, I'm back. Actually, I think a better way to do this is check if the char is in our acceptable range of inputs. So, if first name, first character, which we know exists because it's not null or empty, otherwise it would have returned here and not continued. So if first name 0 is less than or equal to uppercase Z, actually let's just simplify it even more. Let's do if char to lower is less than or equal to Z. No, let's do it this way. Let's do a short circuit and return if it does match these conditions. Okay, if char to lower first name character 0 is greater than Z, or the same thing is less than A, so if it's outside our range, return 0. So you can see this hashing function is useful for English first names. If we have some weird languages coming in, or people are trying to break the system and passing in unexpected input, this is just going to send them all to bucket 0. So bucket 0 might become very large compared to the other buckets, and that's going to decrease the efficiency of our algorithm, but it's still relatively fast compared to scanning a list. So that's fine for this exercise. Okay, now you can see we also have many references to char.toLower first name character 0. So I'm just going to set a new variable, char first char lower case equals this, doing a bit of code refactoring. So it only has to execute this once, and then we have it stored in a variable. That looks good. Possibly, I don't know. Let's try it. Inaccessible due to its protection level. I'm gonna right click, go to definition. So this constructor is not public. It should be public. Looks good. So let's try this. We have our hash table. Store John, which is a baker. Bucket index, my hashing function. First name John. Is it null or empty? No. Get the first lowercase character, J, which has an integer value of 106. If first character is greater than Z or less than A, return 0. We're good because it's in the range of A to Z. Subtract the value of A. And actually, let's just real quick, let's see what that is, because I can never remember. 97. Okay, so you subtract the value of the character A, which is 97, to get it in the range of A to Z. Return it. Bucket index is going to be 9. Kyle's buckets at bucket index 9 is, system index out of range exception. Index was outside bounds of the array. Okay, so what's the problem? Kyle's bucket has 5 elements. Okay, this is the problem. So I'm going to stop it. So I forgot to increase the number of buckets because we're going to accept values of 0 to 25, one for each lowercase alphabetical character. We need 26 buckets. That should possibly fix it. Let's try again. And debugging is a huge part of writing code. This is normal. I don't think I've ever written a piece of code that's run perfectly on the first time or on the second time. I usually have to fix 3 or 4 bugs every time before it starts working smoothly. So let's try it again. Bucket index is 9. Get the bucket at bucket index 9. And if you look at the array, they're all null. So this should be null equals null. We're going to create a new bucket at that index. Looks good. Let's see if it worked in the array. There it is. Bucket items dot add, our new item. Good. We're going to do the same thing with Bill, Kathy, Frank. Now, before we do a retrieval, let's kind of see what's going on here. We're going to inspect it, and we see there's 1, 2, 3, 4 buckets with values. That means that, and this, if you look, this first one should be A, B, C. So we have Bill and Kathy probably, D, E, Frank, and then so on. So the first one, let's open it up. There's one item. First item is key of Bill, value of farmer. That's correct. That's exactly what we thought would happen. So that's good. Let's see if we can retrieve it correctly. Get Frank's job. First name, get the bucket index using a hashing function, which ours is very simple. Bucket index is 5. That makes sense for Frank because that's the 6th letter of the alphabet. Right? A, B, C, D, E, F. Yep. Get the bucket. If bucket is not null, which it should be not null because we stored Frank, for each of the items in the bucket, there's only one, so this will be a very fast iterative process. If it equals it, return the value. Frank's job is cashier. It worked. Perfect. Everything worked swimmingly. Now, couple things I want to show. Let's test someone who does not exist. Let's get Tim's job. Hash table.retrieve Tim. This does not exist, so this should give us a null string, right? That was what we intended. Another thing. Well, let's run through this first and see if it gives us the intended result. Start. It's going to do everything. Get to this point. Tim's job is null. Perfect. All right. So let's go back to the PowerPoint. There's another slide I want to show. So if you look at this, these are two distributions of items in our in a just theoretical hash table. The first one has two items in each bucket. So you only have to iterate at most two items to find the one you're looking for. Now this one below has very sparse, not spread out items. This bucket in particular has 8 items, so you would have to iterate 8 times to find the item you're looking for. Now the total items are 6 plus 4 plus 8. That's 18 items. So it's better to iterate through 8 items than 18, but it's still not as good as iterating through just 2. So this is a bad, there was a bad hashing function used for this hash table. And I kind of want to show an example of what this can kind of cause and why you want to go for something more like the top value and get an even distribution among all your buckets. So let's do an example of that. For our case, we're doing the first name. We're using the first letter of the first name as the bucket value, bucket key. So let's add a bunch of B values. Let's add Barry, who is a frontiersman. That's a job. Let's add Buck. He is a nurse, a male nurse. Let's add, what's another B name? Bill, Barry, Buck, Bob, and he is a salamander. That's a job. So if we search for Bob's job, something odd might happen. Well, something expected if you've been following along pretty well. Let's actually do that. Let's go through the search. So retrieve Bob. Bucket index equals 1, because 0 is A, 1 is B. Get the bucket. Now let's inspect the bucket and just take a look at it. There are 4 items in there. So this bucket is getting a bit swollen. There's a few more items than we'd like in there. If you look at the other buckets, there's so many null ones. It'd be better if we could spread them out over the null ones and have fewer empty buckets as opposed to one that's heavily soiled, as we do right now with all the B's. So let's, if you watch this, it's just going to iterate. And best case, if you're searching for Bill, it's going to take 1 iteration. If you're searching for Barry, 2, Buck, 3, and Bob, 4. And if you can imagine this list getting massive, because B is a very common first letter in people's names, this list will get very massive, and it decreases a lot of the performance that we gain. Now, it's still better than doing a full list search, but it's not as good as it could be. So we're going to go 4 times through this list until we find Bob, I think it is, which Bob's job is a salamander. We got it, but keep in mind that performance hit. That's a very important concept of hash tables, and you want to spread out your items throughout your hash table and keep your buckets evenly loaded, evenly soiled, you might say. All right, before we end the video, there's a couple notes I just want to go over. Notes section. So in our example, we use the first name to identify unique individuals. Now this is bad because what if you have 2 people who are named Bob? That breaks our storage idea, because you'll have 2 items in the same bucket with the same name. How do we know who is who? So we need something to keep these. We need to keep these people more unique. So instead of using a first name, what could we use? And I implore you to explore possible options. I'll give a couple, but be creative. Maybe send me emails with more options. We could use full name, which is also not going to be unique entirely. It'll be more unique than first name, but not completely unique. We can use the full genetic code of the person. which will be somewhat unique unless there are clones of that person. And I know that the government is cloning people and sending them into the general public, and you know it as well. And so that's not completely reliable. It's more reliable than using a full name, first name, but it's not completely reliable because of the clones that are out there. Now, the third option, I want people to really seriously consider, because this has other effects that are positive. We could implement an authoritarian regime, topple the existing government, and assign unique ID numbers / physical barcodes to each citizen. Well, citizen is in double quotes because they're not a true citizen. They don't have rights. This is an authoritarian regime where the elite have power. And I think we should consider doing that, heavily consider that. The final option that I thought of is social security number. That is relatively unique as far as I know. So that's a good one, but you got to keep that secret. So that brings in other concerns of possibly encrypting and decrypting it before we search. So that could be a bit less performant than we'd like. So possibly just an ID, just an integer ID. So consider option 3. Talk to your local politicians, talk to your families about that, and let's see if we can get that going. The final note that I have, there's a bunch of notes I thought about, but these are the only 2 that are worthy of being mentioned. What is a better hashing function to create equal spreading of items among buckets? Because using the first character of the name is not ideal. Now, another option is you could just add all the characters up together and divide it by some number, and the number of bucket divided by the number of buckets, and use the remainder as your index. That's an option that I think is pretty common. There's a bunch of other options online. Try and think about some other options that work for you, that give you equal spreading. And again, well, not again, because I haven't said this yet, but depending on the scenario, depending on your application and the cases that you're dealing with, this hashing function may change. Because if you're dealing with person's first names, that's going to have a different spread for any algorithm than dealing with a person's phone number or social security number, because the numbers are different, the formats are different. So the same hashing function may not work for every single case. So keep that in mind. That's all I have to talk about. Thanks for watching. Goodbye.